How can you debug dangling pointers without performance overhead? Imagine catching a sneaky bug in your program without slowing everything down. That's the goal when debugging dangling pointers efficiently. Dangling pointers happen when a pointer still points to memory that has already been freed. This can cause crashes, data corruption, or unpredictable behavior. The challenge is to find these issues without adding heavy performance costs. So, how do you do it? Let's explore some proven methods. First, hardware-assisted memory debugging tools are a game changer. They use your computer's hardware features to monitor memory access. For example, some modern processors support watchpoints or memory protection mechanisms. These tools can halt your program immediately when a freed memory location is accessed. Because they rely on hardware, they cause very little slowdown compared to software-only checks. This makes them suitable for testing environments that mimic real-world performance. Next, selective or sampling-based instrumentation helps reduce overhead. Instead of checking every memory operation, you can monitor only specific parts of your program or sample memory accesses at intervals. This approach catches many dangling pointer issues during testing without bogging down your application. It's like setting a few traps rather than monitoring every inch of a large field. Lightweight static and dynamic analysis tools also play a key role. Static analysis examines your code before running it, flagging potential dangling pointer risks. Dynamic analysis, on the other hand, can insert simple checks during runtime, like setting pointers to null immediately after freeing them. This practice is cheap and effective because it prevents accidental reuse of freed memory and makes bugs easier to spot. Another simple but powerful method is pointer nullification. After freeing memory, immediately set the pointer to null. If your code later tries to use that pointer, it will crash quickly, revealing the problem. While this doesn't catch all dangling pointers, especially if copies of the pointer exist, it's a low-cost way to prevent many issues. Using smart pointers or automatic memory management is also highly effective. Languages like C++ provide smart pointers that manage object lifetimes automatically. They keep track of how many references exist to a piece of memory. When no references remains, the memory is freed safely. This approach eliminates most manual errors and adds no runtime overhead in releases builds. Specialized memory allocators can help too. These allocators delay reusing freed memory or add metadata to validate pointers on access. For example, some use tombstones, markers placed in memory, to detect invalid accesses. They balance detection capability with minimal performance impact by only checking metadata when necessary. Finally, compiler instrumentation can insert checks during code compilation. These checks use lightweight metadata to verify pointer validity at runtime. They catch dangling pointer use early, with less overhead than full-blown debugging tools. This method is especially useful during development and testing phases. To sum up, combining hardware-assisted debugging, selective checks, static and dynamic analysis, safe freeing practices, smart pointers, specialized allocators, and compiler instrumentation provides a robust way to debug dangling pointers efficiently. Use hardware features during testing, adopt good coding habits like nullifying pointers, and leverage static analysis tools early. In production, relying on low-overhead detection methods and safe programming practices. This way, you keep your programs safe and fast while catching those tricky dangling pointers before they cause real trouble.